Okay, so then let's solve the ODE. So let's bring out the constant stuff and just make it a little clearer. So it's minus 2/15 u infinity squared. Now this is d delta m dx is equal to minus 2 mu u infinity over rho delta m. All right, this is a separable equation, right? We have dx in the denominator here, and we have delta m. So we could bring the delta m's together and bring the delta x to the other side. And doing that, we would get this equation. We would get delta m d delta m is equal to 15 mu over rho u infinity dx. Right, so that's our ODE. We can now integrate this. So we would integrate the left-hand side with respect to d delta m and the right-hand side with respect to dx. What we need to do, though, is let's do this as a definite integral, because we want to do this from the surface to the edge of the boundary layer. So for sure here, we know this is going to go from delta m equals 0 up to the boundary, which is delta m. So 0 up to delta m. When you do that, I guess you have to have a corresponding dimension that goes with the x-coordinate. So the way to think about that is when delta m is 0, what would x have to be? X would have to be 0. So 0 here. When delta m is delta m, what does x have to be? Well, it has to be x, right? It's the coordinate that goes with that. So it's a little bit circular, but that's kind of the way it works out. So you integrate from 0 to x. Okay, so we do that. It's a definite integral. We end up with the expression delta m squared over 2 is equal to 15 times mu over rho u infinity times x. Solving then for delta m, we get delta m is equal to the square root of 30 mu over rho u infinity x times x. That's what. And we've kind of done most of our job here. We now have an expression. Give me a position x, I can tell you the boundary layer thickness, right? Okay, so then what can we do with this? So let's plug this into the shear stress equation. So again, remember our shear stress was, in the assumed form, is 2 mu u infinity over delta m. So now if I plug in my new expression for delta m here, I can compute shear stress at the surface. I do that, and I would get tau s is equal to 2 mu u infinity times the square root of this thing inverted, so it'd be rho u infinity over 30 mu x, which leads to tau s is equal to square root of 4 mu rho u infinity squared over 30 times x. Okay, so that's shear stress. Now you know the shear stress at any position x with this assumed velocity profile. We could maybe go further and look at how does this compare to my coefficient of friction, because normally your correlations and stuff are in terms of friction coefficient. So let's use this definition with respect to the friction coefficient and then compare that to the known Blasius solution. So plugging this into the friction coefficient relationship, so we say Cf is equal to 2 tau s over rho u infinity squared. That's just the general relationship. So plugging that in, we would get this stuff. It kind of simplifies down to what? The square root of 16 times mu over 30 rho x u infinity. This, where am I? This over here is one over Reynolds number. right? Rho, out characteristic, U infinity over mu. And then I just have some constants there. So actually this, in its simplest form, is CF is equal to 0.730 over the square root of Reynolds number with respect to x. Okay, so comparing this to the known solution, what is the known solution? The Blasius solution is, sorry, my handwriting today is something else. Sorry, Blasius solution. Speaking of handwriting, this up here is 16 thirtieths. So the Blasius solution is 0.664 over the square root of Reynolds x. So by assuming a velocity profile, which is a quadratic polynomial, we ended up with this relationship. What is the difference between these two? Well, it's the same form, everything over the square root of Reynolds x. The only difference is this coefficient, right, this constant. And how different are they? Well, I guess about 10% different. So my error in using this approximation is about 10% for this example, right? 10% error. It's kind of good, right? It's not that bad for an approximate technique like this. A couple notes on this, I guess. If we would have gone through and done the linear assumption, so linear would have been something like, let's see my note, 15% error. If we had done the third order, that would have been something like 2.5% error. So yeah, I guess you have this trade-off, right? But maybe it's good enough for what you want to do. Any questions on that example? Yeah.
So we had done the two.
Yeah, or if there's something else about the flow that you wanted to enforce, like what else would it be? Like maybe there's a derivative of velocity at some point that you know, and you want to, you can enforce really anything you want, but those would be the conventional ones that you'd start with.
Okay.
Yeah. And you can do the x momentum at the, say it would make sense to do it at the surface, it makes sense to do it at the edge of the boundary layer, kind of to start, and then other places after that. Okay? So somehow today went really quickly. Hopefully it went just as quickly for you. What we'll do next time is we'll go through this for the energy equation in terms of temperature and kind of get the same type of result.